Good evening, everyone, and welcome. I think you all know me by now. Jonathan Massey, Dean and Professor here at the A. Alfred Taubman College of Architecture and Urban Planning at the great University of Michigan. Thanks for coming tonight to our lecture by Marc Simmons of Front. The real introduction is going to come from Jeff Toon, our Associate Dean for Research and Creative Practice and an Associate Professor here and a longtime colleague and friend of our speaker. I thought I would just say, highlight one thing in handing the microphone off to Jeff, and that's the space that this talk occupies in the landscape of professional expertise, research, and teaching and learning that we are focused on here at Taubman College and at the university. When I was out at California College of the Arts in San Francisco, I got to work a bit with another principal from Front, Na-Min Ra, or Mike Ra, who leads the Bay Area practice of the firm, or their office out there. And he gave a lecture at CCA called Materialistics that really shaped my idea of one area of research and teaching that our fields could really benefit from. And so this idea of materialistics was the intersection of materials science, engineering, logistics, and supply chain with design. Essentially, one of the ways I think about Front is as one of the leading companies expert at bringing together questions of the deflection of steel and glass under loading circumstances, the environmental performance of glazing and other components of a building assembly, with questions of supply chain and manufacture and logistics. Is the glass going to be made in Germany, slumped in China for installation in Ohio? Is it going to be designed in Hong Kong for a team in Stockholm that's going to install it in Argentina? And what are all the stages along the way in the sourcing, the designing, the manufacturing, the shipping, and the installation? Will the curved glazing members be able to tip into place beneath a fixed steel member that they attach to, or are you going to have an oh shit moment when you get the glass on site and realize you have no way to install it? So materialistics came to life for me as really a missing space in our practice landscape and our educational landscape, and because it brings together all of these different skill sets. And so one of the things that I'm inspired by here at Michigan is that some of the faculty at Taubman College are working with colleagues in civil and environmental engineering and in other fields here on campus, as well as with industry partners beyond the university, to develop expertise in that area. Not necessarily calling it materialistics, but really targeting that nexus. It's a very powerful space for innovation. And so when we talk about building sector innovation here on campus, that's the kind of work we're talking about. And it's exemplified in some of what our faculty are doing and in the work of tonight's speaker. So Jeff, welcome up to the podium.
Thanks, Jonathan, and good evening, everybody. I'm really excited tonight for two reasons. First, because I'm delighted to be able to have the opportunity to finally introduce Marc Simmons in his first visit to the University of Michigan, where we've been working on getting him here for quite a while. And second, because of the context that's created the opportunity to have him join us tonight, which is the establishment of the Guardian Taubman Research Alliance, a new partnership aimed to stimulate innovative thinking regarding the futures for glass in the built environment. I first met Marc in 1994, when we were both students at the University of Waterloo's study abroad program in Rome, Italy. Marc and his partner Elaine, who were joining our class after a working stint in Hong Kong at Norman Foster's office, came to join the program. And the Waterloo program at the time had a strong emphasis on cultural history and landscape, and a kind of representational interest in deep time and materiality. So there kind of was studio culture amongst the students of doing these heavily rendered, intense sections and drawings aiming to embody those characteristics, and where better to do such things than in the ancient landscapes of the city of Rome. I can remember Marc pinning up his work for our first project review of the term, 5 square, precisely executed ink-on mylar orthographic drawings of his proposal for an elegant and minimal glass pavilion, including, as I recall, a 1:5 detail complete with a spring-loaded tensioning bar as a way of describing the project. And this was clearly someone with a particular vision and unique expertise. I can still remember the image of this precise, transparent volume set against the fecundity of Rome. In hindsight, it is hardly surprising that shortly after graduation, Marc founded Front, a design and engineering consultancy focused on the development and delivery of advanced building facades and systems, now with offices in New York, San Francisco, Seattle, Hong Kong, London. Front is the most highly sought after design consultancy in the world. From the CCTV headquarters in Beijing, to the Amazon Spheres in Seattle, to the Stavros Niarchos Foundation Cultural Center in Athens, Greece, by Renzo Piano, to the Toledo Glass Museum and Grace Farms in New Canaan by Sana, Front Inc.'s collaborations have produced some of the most innovative and important architectural expressions of our time. And so we're delighted to have you share your work and thinking with us tonight, Marc. I'd also like to thank Sheldon Davis for his role in being able to bring Marc to campus. Sheldon is Vice President of Research for Guardian Industries, one of the world's largest float, value-added, and fabricated glass product manufacturers, with whom we have recently co-created the Guardian-Taubman Research Alliance. And Marc's visit to campus to participate as an expert advisor during a research workshop tomorrow produced an occasion to enable him to speak with us tonight. So please join me in welcoming Marc Simmons.
Wow, that was extraordinarily flattering. The most sought after consultancy in the world, if only. Oh, password's incorrect. Oh, there we go. Okay, so everyone's hearing me really well? Okay, great. Okay, so as always, I have a little bit too much work to show and too many slides, so I'll try and keep a kind of upbeat pace. But first, thank you to the Taubman College and to Guardian for sponsoring my visit here, and thanks to Jonathan and Kathy, Katie, and Jeffrey in particular for enabling this and for the workshops tomorrow. Okay, so I'll just go to a slide. This is, of course, the work of Rex, 2050 M Street in Washington, D.C. I never get time to present this project, so I decided to put it first. And it's almost finished. There's a lot of press coming out, so it's kind of timely. But maybe just a little bit first about Front. It's a multidisciplinary engineering consultancy kind of founded by architects. We're actually only about 40 people in those 5 different cities. So we're kind of spread pretty thin. But part of the reason why we felt we had to have a global footprint is the same reason that Guardian Glass Industries has a global footprint, is we need to be kind of like at least in 3 major continents around the world, because all of these projects have materials being made anywhere, testing anywhere, you know, the project sites could be anywhere, the architects could be anywhere, and the sponsors of the projects could be anywhere. I mean, if we're working on about 100 projects simultaneously, which we do, we might have about 4, 5, 6 cities involved in any given project. And so, trust me, like I'm now 50, and I would have suffered from total burnout had I had to kind of continue up that kind of travel pace. So having a geographic location in 3 continents is like, thank God, we can actually sustain the kind of level of effort that we entails the kind of projects. As Jeff kind of implied, the essence of why we started the practice is simply to do good work. We didn't start as a kind of like idea of a certain kind of practice or a business. We just said, we want autonomy, we want to work for ourselves, we want the right to be able to do ridiculous competitions, we want to collaborate with people on projects that don't make money, we reserve the right to carry ourselves forward by paying ourselves nothing or having a banner year where we pay ourselves a lot. But the point is, it's a kind of like it's a culture of designing and making and collaborating that is the way we wanted to live. And that's why I don't think it's such a scalable business, because it is very individually driven. And the way Mike conducts projects might be a little bit different from the way I do it. But we're totally kind of discursive and messy about how we do work. And even though we understand that the whole industry is highly codified in terms of nomenclature and terminology and contracts and how things do, of course, if you blow that all up and you really kind of like the Matrix, like Neo, you actually see it all kind of like in first principles. You actually, if you understand the logics and the economics behind, and the cultural aspects behind the way the entire global construction industry and design industry is actually structured, then it's really exciting. You start to inhabit every project from first principles, like who is the client? What are their value sets? How do they spend their money? Where do they get their money? And then why did they choose that team? Why am I part of that team? And then the whole thing kind of begins to kind of sort of unfold in this sort of beautiful way. Sometimes it's awful, but that's usually because there's awful people involved, in which case you just run away. I should say something about that. My father-in-law is a wise old Chinese dentist who basically gave us some advice in running our own business. At the end of every year, just survey all of your clients and fire the worst 10% of them. And that'll solve 90% of next year's problems. And it's a kind of interesting way of working. It's all about kind of people and karma, and you know, one good turn deserves another. And often what happens is beautiful projects kind of happen. Anyway, so you've been looking at this slide too long. Oh, it's the same thing. Oh, look, it's the same thing again. So I'm rhetorically just basically showing you the complete suite of rendered slides that Rex produced. So the key thing is this is a Tishman Speyer project, one of the largest developers, headquartered in New York City, but out of their DC office, sponsored by a guy named Rustam. He's our client. And this guy has a speculative commercial building that did not have a tenant. This is a pretty big risk in the DC market, which is not the New York market. It's not cheap, but it's not the same. I mean, your development costs are pretty high and your rents are nowhere near as the same as Midtown Manhattan. And Joshua put together, Ramus that is, of course, this is a kind of competition level concept design to try and secure the project. And with these images, we're all like, can we actually do this? Like pinch yourself, like probably not on a commercial budget, but it's actually really kind of interesting and sweet. And we had to go in front of Rob Speyer and Mr. Phillips, who's their kind of dark lord head of construction for Tishman Speyer. And the idea that this was even kind of viable technically, let alone on budget, was deeply, deeply suspect. But Rob realized, I think, that it had a kind of certain je ne sais quoi that maybe in the market actually could fly. Is a little bit over-optimistic, but not far off. And the whole idea was like, can you do a speculative commercial office building with all curved glass? Do the optics, are they sufficiently non-distorted so that you don't completely turn it into a kind of like a fun house environment from a tenant standpoint? Because most tenants would be like, are you kidding me? Like, I look fat all the time, I'm not gonna be in that building. Or the kind of like Vignoli death ray effect where the sun comes down and concentrates on the ground and melts the Jaguar hood. You know, there's all those kind of concerns. Fortunately, with a cylindrical geometry, we don't have the same concentrating effects. We did the study. So there's that kind of first part where everyone says, and actually with Rex, it's a lot like this. When we work with projects, sometimes, particularly with OMA, there's no design until 20 iterations later or more as you go through a process. And we've done like over, I think, 20 collaborations with OMA over the years, and we have internalized that sequence. And with Josh, who of course comes from that mold, having managed the Seattle Public Library project before he started Rex, amongst other things. Some projects are kind of like, you have no idea what it's going to be, like the Wiley Theater in Dallas. Like that's a project that was completely designed from the inside out. The facade was kind of like a remnant after the fact, after the machinery of the theater really had to work. Whereas some projects like the Perelman Center for the Performing Arts that we're doing, this particular project 2050, were almost like these singular visions at the beginning of the project, right at the concept stage, that everyone bought into. And then the task downstream was a question of, can we do it? How do we do this? Which is an interesting thing, to actually have a very clear goal. And then the process is a kind of different way of thinking about something than the kind of like, exploration, throw it away, exploration, throw it away. Here, the question is, okay, is it viable? And what's the cost? And everything is about that. And so while you're looking at these, obviously, rhetorical finite element modeling shots, which everyone has, the question is, what's the greatest risk? Right? When you're working with a developer project, frankly any project, but developers are particularly attuned to this question, is where's my risk in this process? Because I do not want to get to the end of the process and have everything blow up for me. Either it doesn't work or it's out of budget. You got to manage that whole process. So you may be accustomed to the expression of, Lloyd Hunt. Remember Lloyd Hunt? Lloyd Hunt taught us the 3 Ps. Proprietary, performance, and prescriptive. Prescriptive, proprietary, and performance. Those are 3 forms of contracts, and 99% of the facade world actually works on the basis of performance-based design in the building envelope world. And that's why the industry is so complicated, because you as designers and consultants are basically designing something that you hope to God a contractor is going to fully engineer and realize on the other side of the table exactly fulfilling all of your aspirations. Now that is a dark art, to do that kind of handoff and transfer and to get everyone kind of working, which is why things like design assist have come into being, where you basically say, in order to do that, we need to push the contractor further up in the process. Of course, the CM and GC, they're guaranteed. They're at the beginning of the process, and we all need them right there on almost any job, frankly, now. Whereas the facade specialists, as contractors, are moving up towards the design development stage, and sometimes earlier, in order to get a kind of certainty in terms of the project delivery. However, many people on the owner's side, whatever their nature is, know that they are giving up commercial leverage. So the question is, you bring someone in and now you have a one-to-one relationship. You hope you work to budget, but it doesn't always kind of work out that way. And often what you don't get is value. You might get 50 cents on the dollar because the person that you're partnering with has a kind of conflict of interest, which is you're advising them on design and cost. At the same time, they need a margin to preserve and to deliver the project. So design assist itself is an art form. So this is not that. This was basically saying the biggest risk is the glass. What is the cost of the glass? What is the architectural quality of the glass? The optics, the tolerances, what is the glass? And how do you find that out? At schematic design. So you just do, you go right to the end of construction documents, you pull the whole process forward, and then basically you do what we call a prescriptive design. You don't do a performance-based design, because performance-based design is basically saying, here's all the things I need you to comply with, and this is what I want it to look like, but you figure it all out. We're not going to do it for you. And the contractor has to figure it all out. But prescriptive design is like really old school. It's like 1950s curtain wall, when someone actually drew a line and they said, build that. And I don't really care if it works, but you're going to build that because that's what you're being instructed. Don't think about it, just go and make it. And then you kind of respect people for making it, hopefully well. But these days, of course, you need all of the performance. So we, of course, as a company, we're like a little industrial design company for envelopes. 75% of our work is for owners, but 25% of work is for contractors and facade fabricators, whereby we do full prescriptive design and engineering. So we just flip that into the normal working for Tishman Speyer, and we just say, okay, we are going to fully engineer this piece of glass. We just say, okay, how many layers? What is the energy performance? What is the aesthetics? How many coatings do we need? What are the sealants, the tapes, the laminates, everything? We're going to figure it out one-to-one as if we are the sign and seal engineer record, and we are going to comply with energy code, and we are going to do everything right from a fabrication standpoint. Meaning we're not relying on the contractors to tell us what the glass should be. We're just saying. And then working with Rex, of course, we figured out exactly what kind of coatings we want. We have two. We have a hard coat silver that goes right to the edge on surface 2. The inboard is laminated. And then we have a sputter-coated low-E coating on surface 3 to meet the energy performance. But we have this kind of like Dan, by the way, the coating is the same coating that Dan Graham uses on his kind of sculptures. Anyway, so moving right along. With that glass engineered, the second thing that we told ourselves, being experienced adults in the room, is that this has to be a one-pass installation. Now, anyone in the industry who's in curtain walls knows what that means. We're going to set the panel, all the dry gaskets interlock with each other, and the beautiful thing, the miracle about unitized curtain walls, if nobody's taught you it, is that you have these kind of two sides of a frame that fit together, that when they fit together, oh my God, the building physics works. It's a drain joint pressure equalized system that actually has all these kind of wonderful characteristics that resist water. It's actually thermally isolated. I mean, and actually it forms a composite structural element. And now all we do is have arguments about anti-buckling clips. That's essentially the level of discussion about this kind of stuff. So, unitized curtain walls, one-pass installation, seal the stack joint, the four-way joint, and then keep going, keep going, keep going. But never are you coming back to the outside of the building to apply caulking or to do multiple layers of installation. You're never doing adjustments for tolerance. So on buildings like Grace Farms, which is 1 story tall, we do that. We have a caulk joint. On Toledo, we have a caulk joint. 1 story buildings, easy to do. But if you have a multi-story building with unitized assemblies, the economics of installation mandate that you do a single pass installation if you're working for a developer. If you have a big budget with an owner-occupied building, maybe you can do something a little bit more laborious, but single pass install. So how do you do a frameless glass panel where the glass is actually doing the engineering spanning work while having it fully framed with a drain joint pressure equalized interlock system? And so this is not a frameless system, but it is mullionless. So the mullion implies that the mullion has a kind of profile that is actually resisting the wind, and the glass is only spanning sideways to the mullion. In this case, the glass is actually doing the work from top to bottom, which is not much of a miracle. We're doing like 30, 40 frameless foot panels now on specialty projects. But to do it on a commercial office building is pretty unusual. And then the frame is actually along for the ride. It's bonded to the glass, not the other way around. But it is still a 4-side fabricated frame. And the key thing for us is that the tight tolerances of the fabrication of aluminum, which is basically plus 102 millimeters, means that the glass tolerances for curved glass, which are looser, can be absorbed within the frame, but not at the joint. Right? So the frame, when it goes in, is perfect. The glass is softer. And this won Mr. Phillips, the Dark Lord's approval. He was like, that is the shit. Because you've saved me money, you've guaranteed the aesthetics, and no one's ever done it before. So this is great. So here we have our joint. Now, one thing that you'll notice is this little thing here. It's one of the fine aesthetic details of this entire project. This is more mise than mise. With a unitized curtain wall, you always typically have a reveal between the two halves. That's the kind of IM-pay, the Foster way of doing things. It's like the panels come together, there's an edge adapter, and then there's a shadow reveal. This is like, no, we're going to occupy the gap with a knife plate of shiny metal. And somehow it's the continuation of the curvature of the glass to that point of manifestation. Super sharp. That's what we want. So the unitized joint is actually deferred to one side. And of course, that knife blade is overhanging the way the joint works at a kind of really tiny scale. I only have one slide like this in the entire presentation. I won't leave it up long enough for you to read. But now the moral of the story is, how do you take out that risk? Now that we have a hypothesis, and it is a hypothesis, of a kind of unitized, mullion-less, prefabricated, curved glass, base-supported wall assembly. Most curtain walls are hung, right? This is base-supported. Now, with our prescriptive engineering for the glass, we went out to every curved glass manufacturer we know in the world, and we know them all, and we basically say, here's the product we want. We want you to make 2 panels, identical, mount them in a frame, and we will pay you. How much money do you want to do this? We don't want to owe you anything. And they asked for $5,000 or $26,000 or $50,000. We didn't care what they were asking. And Tishman Speyer was enlightened enough to just pay them all. And then we went around the world to basically China, Mexico, Italy, to look at these different pieces. And theoretically, they're all identical, right? It is exactly the same coatings. It is exactly the same dimensions. But of course, those in the glass industry might appreciate that the anisotropic effects are different, the quench marks are different, the roller wave's different, the overall global warp and distortion in the panels is different, the quality of the butyl on the edge seal is different, everything is infinitesimally different. And it's not to say any one of these companies can't do a fantastic job, they can. But of course, having a direct relationship with the glass fabricators, we also ask them, well, we've got like, say, 10,000 panels or whatever we have on the job. They're all identical, maybe some length differences. What's your price? How much? Anyone here want to guess the variation in cost for the exact same product at this point in the game? It's like the Price is Right. Da, 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 da. Come on down. Hands up. 30 to what? 30% delta? Oh, you were talking about percentage range. 150 percentage. Now, Guardian, who's not really a key fabricator, but glowing in the glass industry, is like, how can the downstream, I mean, our glass, are selling it at like X dollars a square foot. How can these guys then charge like, 150% delta on the fabrication? How is that even possible? Well, we know the industry is like, it's nuts. And also the price changes depending on like which day of the year you ask them, how busy they are, how they perceive the job, whether they think Tishman Speyer's difficult to work with, quote unquote, do they pay their bills on time, blah, Everyone's assessing a constellation of cultural, economic risks as they price the job. Anyway, the fact is we got a number from $42 to about $86 a square foot. And then Tishman Speyer with the CM and with us negotiated it down to $36, and we gave the job to Tianjin North Glass. So, and they had the best quality glass, best quality with quench marking and all that jazz. And so then that 36 was put in our pocket, and then we bid the curtain wall. We went all the way through now to a fully conformed set of 100% construction documents. Because we understood, we talked to various fabricators beforehand, would you still bid this job? Will you bid this job? Are you interested in this job? And by the time the bidding actually came out, we had 7 fabricators willing to bid the fabrication of the actual panels, and all 7 were willing to accept the novated glass supplier at the price. However, their margins and markups on that price were theirs. You want to put 15% on that, or 50%, or 100%, or 200%, that's your business. You want to price their commercial non-performance, you want to price in delays to the project, you want to price in extra breakage, whatever you want, you can do that. That's your prerogative. And so we bid it out, and Alberto de Gobi's relatively new company, Fabrica, won the bid, and in classic way, they're like the lowest price, also with the most intelligent responses. We gave up a couple of details, like we allowed the frames to go slightly behind the back of the glass panels where the spacers were. It was actually kind of useful because it's a nice point where you can actually dovetail an interior partition with the glass at that point. And So furthermore, to save money, so the glass novation worked. We got the supply for a number that we couldn't believe. And then because Fabrica is relatively new and they didn't really have a pipeline of work in Washington, D.C., there wasn't really a benefit commercially to them doing the installation. So the CEM had very strong installer relationships and basically negotiated a separate contract on a cost-plus basis with an understanding of kind of certain risks. They're indemnified against certain breakage, replacements, and things like that. So basically you wash it out, and you're basically breaking it up in a way into 3 components, but delivering the final fabrication engineering as single source turnkey. Meaning even though we engineered it as though we were going to sign and seal it, they are still retaining an engineer in Washington who is going to sign and seal in that jurisdiction. So it's still, in a sense, performance-based delegated design, but virtually on a prescriptive basis. But if you actually look at the shop drawings, there's still a lot of evolution. I mean, to give Fabrica credit, I mean, even the bracket innovation that went on is pretty interesting. So I'll just run through, now you've got the whole story. You can just basically look at this like a storybook. So this is a bending tempering furnace, which automatically CNC curves glass, which is now up to 3.3 by 18 meters globally, if you're interested. And we're pushing for projects now that have 18-meter long glass, if we can get it done. So here's some of these rolling racks around the world in different factories. Basically the exact same thing. There's Josh and my guy Patrick. And then we went, after we got the job done and went to Fabrica, we went through the shop drawing process, and now we are at the performance mock-up. So this is our performance mock-up now. You can start to see that kind of like knife plate manifest at the kind of middle. The corner also has that kind of similar detail. And then just a whole series of photographs showing the kind of fabrication sequence. Important to recognize that because it's a single spanning piece of glass, the structural silicone at the top and the bottom is about 2.5 inches thick, which they whinge a lot about the curing time of that. But of course, it generates a couple. It's almost like you can imagine the engagement on a glass balustrade. So the couple at the top actually thins out the glass. So the glasses, the substrates are still only 866. It's actually still very economical in terms of substrate thickness for something that's actually spanning unsupported over about 11.5 feet. But at the bottom, we have a stack joint. So the horizontal, even though the vertical is kind of mullionless, we do have still a horizontal continuous stack joint that is fully drained. And what's interesting about with the panel when it goes in is we have a very deep slide-in bracket that is torsionally stabilized. So when you first install the panel, it actually is rotationally stabilized against falling out. Because most panels are hung. You hook them on, and then they're stable. This one, you're actually slotting it in the bottom, and then dead loading it, and then dialing up the dead load afterwards. Anyway. So you can see the panels, 4-side, fully fabricated, curved glass. And then we're starting to get to the installation on site. This is our beautiful bracket. Those are the curved horizontal extrusions with these kind of slotted in brackets that sleeve in so they don't rotate. And then you have the set screw which dials in vertically, locks in the dead load adjustment. Corner panels, typical brackets. And then the first real panel installations. Now, just while I'm showing you all these images, one of the kind of crazy things about this project is Tishman Speyer assembled 3 sites, one of which was the CBS Face the Nation studios, which had to experience completely uninterrupted operations during the entire construction of the project. How do you do that? So there's a big site, there's the CBS studios, and there's another site. That site fit the CBS studios. So you knock down that building, you build a new building, you move CBS overnight, which includes the new facade. The new facade actually was put on in this kind of little localized area of the building. And then the rest of the building was demolished and then built up over on top of it and meshed together. And then the facade was installed seamlessly as though the other building never existed as a separate building. So this is the kind of stuff we do to enable, there's the CBS component of the project, built and installed first in advance of the rest of the building. This is a good image that really shows you that kind of like knife plate detail there. So the panel's on site. And now because it's geometrically repetitive, it's a real dream just to put in. You can see the smoke seal along the bottom there with the fire safing. And then your first real sense of what this is. So that was the CBS component over here, which has now been swallowed up by the rest of the building as it continues across. And I think the renderings were pretty convincing, but this is one of those few buildings where the optics of the real thing are just like, the fidelity is way beyond the rendering capability, and the real thing is nuts. Like in a way, the thing reflects the street and the clouds at the same time. And the glass actually starts to look kind of double curved. I'm just going to leave you with this image for a moment because it's kind of unbelievable. Like, because of course the concrete is post-tensioned and it's coming to a thin slab and the ceiling is tapered up to that little point that actually fits within the stack joint location. And then of course when you see the corner, you get that incredible transparency of this frameless unitized system. And I've just never seen anything like that before actually. Except for that, like, you know that, what was that kind of speculative model that Mies van der Rohe made? Of that beautiful translucent thing, it's like, yes, nailed it. And we should say, before we move on to Grace Farms, that the building was 100% pre-leased prior to construction by a single law firm above pro forma target. Yes, and that gets you the next project and the next project and the next project. Grace Farms, wow. This is one of Mikey's projects. I love it though. We know everything about it, but it is just a spectacular tour de force. If you guys haven't seen it, go and see it. Toledo's good. This one's a little bit further afield, but make a field trip. It's open to the public mostly year-round. So it was actually commissioned by a benign or evangelical kind of benevolent society who stripped out the kind of religious aspects of what they do to register as a nonprofit. And they do a lot of good in the world, though. One of their biggest focuses on anti-trafficking of minors, and mostly female. So it's pretty serious and very emotional work that they undertake. And so this building is really a community center, just made for their community. And of course, if you've seen the program, it has an athletics facility with basketball courts, and it has a little tea house, it has a library and a reading room, it has a cafeteria, and of course it has an auditorium for presentations. And each one of these kind of programmatic elements is considered as this little pavilion in the landscape that is then connected by this kind of undulating roof that sometimes becomes an actual roof and it becomes a cover on a kind of spongy walkway that's basically a complete mapping of the topography of the land. It's like the kind of dream project in school. We're always like, oh, it's just a building exactly going on the land, and we'll make a pedestrian path through the forest and down by the river. And that's what they actually did. So it's both a nature trail and the building as a kind of route of exploration of the landscape and the topography. And you can see it in a section. So just technically, there's only a few components to this building. Basically, there's the glass, and then there's the timber structure. Silman was the structural engineer for it at Oppenheimer. And the roof is basically this kind of like what's cold-formed aluminum sheet. It really has a roof rain screen on top of a insulated inverted roof membrane. So here's the cafeteria and the dining hall. You can see the regulating lines, this kind of radiating lines here. So all the structure, I think, is Canadian. I think it's Douglas fir, large, beautiful glulam beams that were brought in from British Columbia, trucked across the country. And there's some pretty interesting detailing with the wood. So you can see from the plan here, these kind of like little pipe columns, and those are steel, and they don't fall on the grid. And then there's a bent piece of wide flange W section that just basically undulates gently around the whole thing. You can see through the glass, you can see the flanges of that beam. And the timber trusses, or their beams actually, are curved very gently, but they strangely don't touch the steel. They stop, and then they're coped. And then they sit on top of the steel, but concealed under the ceiling plane. And then they are further coped around the head of the glass detail, because you'll understand this better just by me using my hands and looking at the section. The sections are almost indecipherable. And then as it copes up over that, then it's strong enough to become the cantilever of the overhang. And the overhang is a good way to start a story about the glass, because there is some very special things about this glass that are also unprecedented. So, of course, all the glass is following the curvature. It's all trapezoidal in section, and it's all curved with different radiuses, depending on where it is in the project. And it's all double laminated because it's exposed on both sides. And it's annealed. It's all annealed glass. There is no heat strengthening or tempering in this glass. And that's because it's optically beautiful. Again, there's no heat, roller wave distortions or quench marks or anisotropy, you know. I mean, I love the Apple cube, but if you go and see the Apple cube, the whole thing dematerializes into basically a kind of a cornucopia of imperfections in glass fabrication, which is kind of weird. It's like you dematerialize something to nothing, but then you're kind of left with these artifacts. And if you walk to the Apple cube with your polarized sunglasses on, you're like, whoa, what is that? Not to criticize Tim Cook or Steve Jobs, but by the way, full disclosure, Apple's our biggest client. I'm not allowed to say that, but we didn't engineer the glass cube. Nothing to do with that. Anyway, I'm going to go off track here. You're not recording this, are you? Okay. Really? Everyone records these things. Oh, I'm so glad I can speak freely. So the glass is annealed, like Toledo is annealed. I'm sure all of you have been to Toledo. So Toledo is optically perfect because it's that. And it doesn't have any coatings on it, and this building doesn't have any coatings on it. There's no low-E coatings. But Toledo has the magic of a double wall. It has a cavity. It's got the free desiccated heating from the hot shops, which are working 365 days a year. And in the winter, you know, it shouldn't work. And then, of course, Petroblaze did that beautiful undulating sputter-coated low-E covered curtain. Here, we just have an insulated glass unit. So what we do have here is we have an overhang. The overhang is key. It's a 1-to-1 ratio, and it cuts out so much direct solar heat gain for the summer and shoulder seasons that the solar heat gain on the building is almost negligible, except in the winter when you want the solar gains through the glass. And so with that overhang, we don't have the coatings. It is insulated. Of course, we need the U value to prevent condensation, but we also have geothermal on this building, and we have perimeter heat coming up around the entire edge of the glass for comfort. So that's actually something that's working really well for us. Without the geothermal, it wouldn't make so much sense. So getting back into the glass. Well, there's a radial curvature for the strengthening of the glass. That's all a good analysis, but I don't want to talk about that. What I want to talk about is this. So if you were to just approach a glass fabricator off the shelf and just say, I want a frameless piece of glass, like 13 feet tall, my wind loads are 2.5 kilopascals or whatever. And this is probably where you would end up. Because what people are normally calculating is the heat buildup and the contraction of the air cavity and the in-plane forces on the structural silicone. And so what you're actually looking at is heat buildup here, pushing sideways, putting this into shear, and the length of this structural silicone is actually governed by the shear strength. So temperature variation in here is critical. And if you haven't actually analyzed it, everyone would default to the absolute worst possible case. And you know that also you probably heard about thermal stress analysis for thermal shock. In cold climates, you have a direct shadow onto glass, the glass heats up, and the rest of it's ambient cold. The whole thing fractures by itself right across the middle. It's also another reason why we never use annealed glass in cold climates, because of thermal shock, unless you analyze it, unless you really are in control. And then the great thing about low iron glass with no coatings in it is that it absorbs very little heat from the sun. The sun just goes right through it, or the radiation goes right through it. So the glass itself is not actually heating up that much. And we did very detailed finite element modeling to demonstrate what kind of, by the way, that dimension there is 86 millimeters, and the actual dimension here is 40 millimeters for silicone weather seal, structural silicone, and the spacer. It is the narrowest profile ever achieved for a frameless insulated glass. I know it's a lot of caveats in terms of groups of checks, but we take our little wins where we can, right? Because they're very nuanced. But for Shm, this is it. I mean, if she had her way, or he, to give them both credit, the glass would ideally be a cast piece of undulating ribbon of glass. Can you make that? Not yet. I know Corning's working on their waterfall glass, but it's basically like crinkles with like whenever you touch it. Anyway, so 40 millimeters. And that's based on the building geometry, based on orientation, based on the building physics of this, actually doing a finite element modeling, looking at the cavity temperature range, calculating the in-plane stresses on the silicone, and actually working it out. Then getting our facade contractor, Roschmann, who is great, out of Germany, on board, and then getting Precursa, our glass fabricator out of Spain, on board, agreeing that our presumption is correct, them doing their own calculations to verify that, and then doing empirical testing. So the owner would have to fund full-scale chamber testing, thermal cycling, to really see whether this glass is actually going to crack and fracture. And in the end, it's so far so good, knock on wood. Here's that timber section. So the bottom of the beam is here. It comes up, it copes, it connects to the top of the steel, it copes again, goes over the movement joint, and cantilevers all the way outside. So the insulation is all under here. We have a waterproofing membrane, and then we have the metal cladding up there. And here's our frameless insulated glass panel. Anyway, so the panels are about 8'6" wide, 13 foot tall on average, but they kind of undulate and curve around. But I think that gives you the kind of essence of the project. This is a good picture that captures that articulated steel beam just sliding behind there. Another detail I like about this project is it has a little cedar-faced gutter around the perimeter that just scuppers the water off the roof, like traditional Japanese style. And on the bottom, there's these little pits. Oh, there's my kids. Little circles of gravel where the water just puts out of here, and then these things happen in these kind of like little engineered locations wherever the low points on the roof are, which are really lovely. And then this is, you know, for me, this is kind of like heaven, you know, like the amount of work that goes into like this flush, super minimal, you know, the gradient, this grillage here with the air coming in. I'm sorry, give me a moment. That's the Teahouse. And actually these uplights embedded here are really lovely, basically providing this kind of like warm glowing soffit in the evening. It's really beautiful at night. You can see the way that steel is always like a little pet. It's like a little system that's always there for you. Okay. So for the Sana diaspora, that's what this is. Many of you may know Florian Eidenberg and Jing Liu. Have they come here? Yes. So they're great friends of ours, and we work with Toledo. We worked with Florian on several Sana projects when he was working there. And then he went out on his own just shortly after we did to found Soil, which is in New York, in downtown Brooklyn. And they're doing great. We're still working with them on several projects. And this is the Shm Minetti Art Museum. This is a very short little vignette. But this, I won't talk so much about the design, I'll talk about the procurement. So this is a builder-led project, builder-led design build. Whiting Turner led the bid for UC Davis. That was the way it was done. And so Soil with Boland Sawinski Jackson were the architects under that. We as facade consultants were part of the team, but we're over here. And so the team, and all the other consultants, of course, are bidding the project with a design competition. We're on two teams. We're on Work AC and these guys, and Soil won. And in this context, we're able to kind of spread our wings a little bit more because Whiting Turner, of course, was in for a GMP with a kind of guaranteed design, and they were looking for every possible way to reduce the cost of delivery. And so for this project, we also did full prescriptive design under Whiting Turner. And if we were under the architect, we wouldn't really be allowed to do that. I mean, the Tishman Speyer thing, we were acting as though we did it in order to enable the procurement and then to assign the responsibility. Here, we just did it. And so every one of these Toblerones is a kind of self-structured element that has a certain length. We have a splice detail that actually generates structural continuity from element to element. One of the real cost savings that we found was, of course, because you'd have to fold this, and then you have to weld the seam, you have to pre-perforate it, and then you'd have to post-anodize it after all the milling if we want to actually preserve it. And so our investigations led us into marine-grade aluminum, which is a self-finished grade of aluminum, which is a little bit pricier, but when you net it out, it's much less expensive than the anodized handling after the fact. And so we actually engineered the whole thing based on welded marine-grade aluminum, which was, we generated all the fabrication drawings, and then we did the sourcing from a company called Program in Shenzhen. And then we enabled Whiting Turner to essentially buy wholesale without us being necessarily in the stream of commerce. So we kind of kept our noses clean again without kind of double dealing. And not that anyone really cares about that, but if you do full disclosure, I guess it's fine. But in the end, it kept things really clean. So Whiting Turner was able to buy all the material, they did all the steel locally, and then they hired an installer, and they saved a lot of money. It doesn't always work out that way, but it is one of the kind of stories on this project, and you can see the amount of kind of like custom fabrication detailing and stuff it would take to put this together. And the result is wonderful. Okay. Anybody here Canadian? Only two. That makes three of us. I asked my students at MIT that, what's this building? And they're like, oh, that looks like it's in Prague or something, or it must be in Budapest, or it's like, no, it's in Ottawa. It's awesome. Anyway, so the way we got this job, though, was, this is the story about, this is the professional practice part of the lecture. So if you're a young intern working at a firm, don't piss anybody off. Because one good turn deserves another. So when I was like 20 years old or something, I did a one-year internship at KPMG Architects. Turns out Bruce Kuwabara later served on an organization called ACPIDAR, which is a group that advises on any changes to the parliamentary complex. It so happens that West Block, which is this building, which is the oldest load-bearing masonry structure in North America, it doesn't have a steel frame. It's built like a cathedral from the 1200s, but it's built in about 1860. And this building was identified, was going through a kind of restoration. And then Architecture 49, which is formerly ARCOP, and EVOC, which is formerly Fournier Gershowitz Mas Drolet, they won that bid to renovate West Block. But during that process, they were also advising on the lack of suitability of the current House of Commons and the Senate. And so under Canadian law, a riding for voting can only be so big, and as the population grows, there's like 338 members of parliament now, and the original space is only designed for 200 and something. So they actually really needed to gut renovate the entire center block, which they're doing now for $6 billion. And they needed 15 years to put a House of Commons, and they decided to stick it in that courtyard right there. Now, you might think that putting a giant glass roof, which is blast resistant and multi-layered and operates like a TV studio roof, you'd think that you would have an international competition like the Reichstag or something, like where Norman Foster comes in and does like the Bundestag, right? But in Canadian style, public works is like, seems kind of like a big problem. Let's just kind of keep this under the table, and we'll keep the architecture team that we have already. And then KPMB, well, Bruce Goibarra said, well, I think you'd probably need some design-oriented consultants. And he gave ARCOP our name, and then Norman Gluberman came down to New York and said, hey, can I talk to you about this potential project? And I was like, sure, okay. And this was like just a few weeks after the Canadian Gold Cup win at the Vancouver Winter Olympics. Yes. And we spent an hour talking about ice hockey. And then we said, you got the job. And what's the job? Oh, by the way, it's a new Canadian House of Commons. Well, all right, 9 years later, here we are. So there's probably a little bit more in terms of, what really got us this job was having done the Seattle Library. So they said, yeah, it hasn't leaked yet. They checked the references, and then they said, okay. And you're Canadian, so you must understand ice and snow. Because, you know, this building is going to have a glacier on top of it. And of course, we had RWDI consulting on the glacier. So here's the courtyard. This is quite a long sequence, but I'll go through it really fast. One of the big challenges here is because of the existing nature of the building could not be strengthened as a heritage building, and there's no way to just start threading steel down the whole structure. So everything had to come up out of new foundations in the courtyard with mechanical rooms, committee rooms, and then building up a new boxing ring for the House of Commons. And then all of the structure actually came up and then had to be self-supporting, and it turns out to be about plus or minus 3 inches of relative displacement under seismic and wind relative to the existing building. Now, if you're adding, say, to a neoclassical building like the Portrait Gallery in the Smithsonian or some other equivalent buildings in the UK, it's much easier to deal with the parapet. But of course, this is a neo-Gothic building, and we have ornate ventilation shafts, we have chimneys, we have crestings, we have monstered roofs. The perimeter is a nut-like kind of situation, and the addition has to be blast resistant. Anyway, so this is eventually the kind of structural lattice of the columns that comes in. There's challenges. I won't go into all the details, but this space volumetrically is 3 times the biggest the House of Commons space right now. So the echo in there is really big. There's a lot of requirements for acoustic attenuation to reduce the effective reverberation in the space. At the same time, there is a need, as I said, believe it or not, they assume in wartime, during crisis, the power goes out, you must be heard across the floor naturally, so you have to be able to speak without without artificial speech reinforcement, so the acoustics of the space have to be perfect. And then while you're working with speech reinforcement, it has to be simultaneously translated into any language that you elect. So that is one of the rules. The other thing is 24/7. Whenever there's things in session, it's always broadcast live, like C-SPAN type of stuff. And of course, the sensitivity of those cameras to light contrasting changes governed how much light could come in. So if a cloud went over the roof at a certain moment of the day and the light levels went down and the cameras couldn't react, that's an unacceptable performance criteria. Like, you can't fail on that one. And so working with OVI, who is a lighting Transolar on energy and daylighting, we basically dialed down the amount of light coming through the outside layer, through the baffles, which is the access floor that's in the middle, which is that thin line here. And then we have the undulating lay light system below it. And then there's a kinetic set of motorized louvers that's up just under this layer here. Here it is. So triple seal glazed units, which are blast resistant, operable louvers, the fixed maintenance platform, and then there's the interior lay light that recalls aspects of the original design space, which also has acoustic absorption within it. And now, because it can't load itself on the perimeter, it's not a grid shell. It's not like a vaulted structure. It's actually a truss that's actually coming in from the inside and then cantilevering out. And that's why, efficiently, it has just a big truss in the middle, which is actually like a three-dimensional space frame, that has this geometry that goes from a double curved underside that's all triangulated, from a dome that flattens into a square, which of course is a non-standard geometry, which then gets chiseled like a diamond into flat planes in order to describe that geometry. It's quite beautiful. And then we have those two layers that we sandwich together, and somehow inside the space reservation offset creates the geometry of that steel structure. So the steel inside the attic is generic wide flange kind of steel, very complex steel. And then the inside is all complex welded architectural steel. And so we did all the BIM modeling. We did all of the drawings, 100 sheets of CD details. And we did we didn't do the structural engineering for the roof, but we did all the structural modeling for the roof, because this modeling exercise was outside the capacity of the structural engineer that we were collaborating with, which is Nebojsa Odrovic. So very quickly, of course, all of this was a kind of elephant, rhino, grasshopper kind of flow, and then give you some sense of the kind of exploded perspectival axes sort of the various systems. Now, just as I go on to this, I'll start talking about the procurement. So this was 100% design, bid, build. So 100% conform construction documents, with PCL as the general contractor, and a full handover to a facade contractor, which would handle the steel as well. And the way that was done is they did a very rigorous pre-qualification process, and we thought we'd get quite a few people, including North Americans, but in the end it turned out to be only two companies, Gartner and Sealy from Germany, qualified to do the Canadian Parliament. Sealy won based on cost, but what you're looking at here is we, of course, this is delegated design, but basically to rhetorically tell the contractors that we understand our geometry perfectly, we documented every single panel in the roof. We put it into a totally rhetorical data dump onto a 2D paper sheet that no one could read, because the actual contractual deliverables was not the model or Excel data sheets, it's actually just paper. Of course, the first thing anyone asked for was, by the way, can we have the Excel version of that file? Indemnified fully, can we have your model? Yes, but we all anticipated that we would hand over all that stuff, but of course, without the responsibility for it, which is kind of like, unless you're doing a truly integrated project, contractually, it's the way you have to do it. So these are all the lay light panels. There's 13,500 of them. And then here's the list. And this is the bid pack. And then there's the roof, which is kind of like the Seattle Library. It has 3 lines of defense, except instead of a mechanical pressure cap that's outboard of the glass, this is such a low slope that it's still 3 lines of defense, but the pressure cap is flush with the surface of the glazing. And that's to prevent any kind of accumulation of water or snow or ice, and to allow all the water and ice to drain towards the edge condition. And here's the gutter, which is a massive gutter, which has this cantilevered stainless steel plate that prevents the glacier from basically pouring off onto the existing roof. And then this has 6 lines of heat trace, and it takes all the water back to the inside of the building. And then just some photos of the kind of construction as we're going up. Various performance mock-ups and technical validation mock-ups, constructability mock-ups, and then the actual steel construction. Walter Steel of Canada did all the steel work under Sealy's direction and fabrication drawings. And then Sealy put together these prefabricated frames on the ground. They were hoisted into place. And you can see how it is kind of chiseled into kind of facets as it goes around. And actually, I love this technology. This is very German. There's a blue tension net that actually gets attached to the whole underside of the steel. So the glass installers can walk anywhere on the roof, and then as they finish their work in certain regions of the project and they can start working on the glass, they just start cutting away the net until it's fully removed. But it gives them a completely safe environment to just walk around as one does. If you're wondering what that tape is, that's an aluminum reinforced butyl tape. It's a really excellent sealant, but you don't have to do any caulking work. That's our secondary seal. And then here we are, our kind of low slung roof with the clear stories. And then some interior shots. And this is that maintenance access platform of which every panel is also openable, so you can actually clean all the lay-light glass from the top and to service and maintenance if you want to replace it, so you don't have to get from the underside and the interior of the panels. Okay, I'll leave you with that image for a second. So Amazon spheres, we did this with MBBJ, but we did it as a team with Magnus and Klemensic. They wanted all the consultants to pitch as kind of integrated services, so MKA employed Front as a combined primary structural and envelope consulting team. And this was explicitly meant to be design and sys, so at the end of DD we had Enclose come on board to the project. And so I'll try and go through this very fast, but Jeff Bezos and MBBJ were working very closely on, he expressed an interest in some kind of Kew Gardens, Victorian kind of greenhouse type of environment, but at the same time something that was kind of contemporary. And these are drawings that we did, basically every type of mapping of a sphere that you could imagine. Eventually it's a Catalan series, which is kind of like a soccer ball. Developed into this kind of pattern, and then MBBJ did like all of these variations on Catalan steel until we basically had a kind of basic configuration. And then you'll notice the glass is actually not curved, so it's not a spherical element, it's all flat, and then it's all triangular and trapezoidal nested together, and in some ways it's actually not all concave. It actually oscillates between concave and convex depending on the geometry, which gives it this kind of like particularly interesting crystalline like rendering of the form. Of course, in the big picture, Apple will spend whatever it is, $3,000 a square foot on the entire square footage of its entire headquarters. Google will invest about $600 a square foot in what is a glorified Costco, which we worked on. And then you have Amazon, which says, we're going to build completely conventional grade A office buildings, and then we're going to spend 5% of our budget on one iconic element that is just basically a glorified cafeteria and lounge for our workers. But I tell you, Amazon got more mileage in the media out of this than I think Apple or Google did for their massive investments. I mean, this is Bezos being incredibly kind of strategic about his kind of like iconic investments. And it sort of fits into the Amazon brand of basically being kind of seen to be modest actually from his investors and shareholders standpoint. So I'll just talk about what was interesting is when Enclose started to make submittals, MBBJ and the team were saying, well, there's no way to validate any of this, so we can't comment on it. And so Amazon and their owner rep, Seneca, said, well, we understand that contractually, but we can't accept that. We need to have it validated. So MKA and Front were actually contracted for an additional service, which was to fully model and analyze the primary structure and Enclose's structure and adopting Enclose's shop drawing details, their means and methods, their panelization, not ours, in order to run a parallel validation. So we're still on the owner's side, but as if we are the contractor. So you have these two teams running in parallel. And using our tools like Elephant and Grasshopper and Rhino and automation, we were generating, using the API into Strand 7, basically analytical models that have over 200,000 components being run through 105 different load cases iteratively. And every 2 weeks, we would generate a report of all the kind of non-conformances in the member elements, the bolts, and so forth that actually were being overstressed and under which load case. And this was a very nice symbiotic relationship going back and forth. And eventually, everyone agreed, it was all working. But part of that process is, because these are crazy, this is a kind of trial assembly mock-up. But we also went to a full-scale performance mock-up. And the full-scale performance mock-up was interesting because we were like, who's going to determine that? And then everyone said, well, you guys should. And we're like, okay, so we've got the analytical model. And what we're going to do is we're going to basically data mine the analytical model to find every element that is at its maximum stress. And then we're going to create a Frankenstein mock-up that basically tests all of that and determine where it's going to be hydraulically jacked in order to do it. And so we worked out what the performance mock-up should be, which is basically this thing here at this angle. And everyone agreed. And then Enclose made it. And then they tested it. And it worked. And what was kind of exciting was to see whether the actual mode of deformation in the mock-up matched the prescriptive modeling or the projective modeling that was done in advance of that. And it did correlate very well. But a very interesting non-conventional process. Here's the kind of like predictive model, and here's the actual deformation of the steel under load. But of course, we love to do these kinds of images, which are completely rhetorical BIM porn. And a few images. This is MKA's fabricated steel. Unbelievable. Canron did this stuff. Same guys that did the Seattle Library ages ago. Just gorgeous. It was all painted on site and then glazed. And of course, we had a removable rooftop, which is kind of cute, in order to bring the biggest tree inside. Here it is. I won't go into the whole building physics of this. It's a whole other story in terms of it, climatic control, humidity level, what's good for humans, what's good for plants, what kind of plant selection could actually be in this building to create this kind of environment. It's basically high altitude equatorial, if you need to know the kind of bandwidth for the plant selection. Think the mountains of Borneo. Okay, so that's that. Shenzhen Energy Building, this is a very short sequence because I don't have a lot of process images, but this building, this was started a long time ago with Big, when Big was not big, and we were just getting going, and we knew each other from the Seattle Library. I actually met Bjarke back in like 2001 when he was a young guy, even before he founded Plot, and then of course left that with Julian DeSchmidt and then started Big. And this is moving a couple of years into Big. This is one of their first commissions. It was quite serious. But they didn't have the technical expertise, so they retained us to kind of work as a seconded extension of the architectural team. So we also did all of the drawings, kind of layout, geometry, and so forth. But to make a long story short, it is the Shenzhen Energy Building. So they pitched the idea that it's a folded curtain wall where all of half of the folds basically facing south and west are 100% opaque. Zero solar heat gain, fully insulated. That's a good idea, right? Just selective orientation. And all the north and east are mostly glazed. They actually have an insulated spandrel that's insulated. So you only have about, I'd say 30% window to wall ratio with all of your solar heat gain going north and east. So the energy performance of this building rocks, you know, because this climate is also largely heat gain dominated in the kind of tropics. And just when it was being designed, though, China put into place a kind of like energy SWAT team that went around and started auditing buildings because most of them were non-compliant by any measure. And this one was one of the first that actually far exceeded their expectations. And so eventually it got contracted. And it has some pretty funky things. So it's a basic folded geometry, which of course admittedly increases the developed surface area by about 35%, which costs something. And also, from a passive loss standpoint, it is a fact. But again, as I said, it's heat dominated from the sun. But then they have all these kind of lovely deformations where the relentlessness of this folded curtain wall opens up into these large areas of release on the floor plates with some flat curtain wall zones. But doing all of that is pretty complicated. This is one of these lovely interior images. But I love the drawings on this. So these are the elevations and sections with these kind of crazy undulations, but totally systemized, and then of course you completely wig out. And of course it's all flat panelized assembly, cold formed into place onto geometries that are actually truly double curvature. So it's actually not all cold formed glass, it's actually all cold formed curtain wall, which is pretty unusual. This is like Terry Meyer Boag, sacred geometry. Sorry, inside reference. And then the details are cute. I love these kind of like radiused interiors because this is like a bamboo veneer hook-on material to basically abstract its kind of curtain wall-like quality, and then you just have these glass panels. And they did all these beautiful one-to-one mock-ups with like putting kind of like Chinese classical painting wallpaper on the panels, and of course over multiple panels. When you look at it in one direction, it creates that kind of lovely image. You know, it's a way of pitching it to the client, but actually it looks pretty remarkable, and for a curtain wall, it's not that common. Anyway, I like these drawings. These are the corners, and then there's one where we start collapsing the geometry, which gets pretty messy. From here, you can see it actually begins to start to collapse to nothing. But that's what you need to do. You need to draw all the kind of instances in order to figure these things out. We kind of can't believe they built it, actually. So here's the sample. A lot of people don't know this, but the outside of the solid part is actually 3 white aluminum extrusions that have this kind of rigatino kind of folded texture on it, which gives a kind of lovely extra little kind of layering as a rain screen to the curtain wall panel itself. And this was an idea stolen from Sana's new museum and Wiley Theater and a bunch of other things we're working on with extruded aluminum. And then a few construction photos, and then the finished thing, which again is like more nuts than the renderings. It's like Yamasaki, eat your heart out. You see how it's kind of faceted, right? It's not actually curved. And then from this angle, it's like this kind of sail-like, ghostly kind of building. Okay, I think you get the gist. Okay, another folded curtain wall. So back in 2008, when the economy collapsed, people started asking us, how much repositioning work do we do? We're like, what? What? And we're like, what the hell's that? Reworking existing buildings. Or like, oh, adaptive reuse. And like, well, that word's out of fashion. It's not a commercially acceptable word. We call it repositioning. We're like, okay. So then we did an audit of all of our existing work done to date up until 2009-ish. And we found out that 33% of every project we worked on was somehow an addition or extension or modification to an existing structure. We just never thought of it really as renovation because we were always working on the new component of something old. Because we don't really do forensics of heritage facades and things like that, but we like to add to heritage buildings. And so Brookfield Properties bought this building as part of their Hudson Yards deal. And Amanda Burden, then the planning commissioner of New York City, basically begged them to tear it down. This is like 1968 by Davis Brody Bond. It actually has some kind of dignified qualities to it as a kind of classic brutalist building. But it didn't really weather that well. So here it is, just before being renovated. But it is built like a tank, and it is literally a bridge structure over the rail yards. It actually has 6 facades. It's like 5 plus the underside. And you had to do an energy upgrade and all this. But Brookfield said, look, we're building 2 50-story towers with SOM. We're not going to build another tower here. This building is valuable enough as it is. All we're going to do is reposition it. But it does have some qualities. It is like high floor to floors. It has this kind of interesting waffle slab throughout. Then it had this weird stepping, of course, with these large precast facades with strip window clerestories. And eventually Brookfield said, okay, well, we're gonna reskin the entire thing. We're gonna double the size of the lobby and do all these things and re-elevator the building and do some upgraded mechanicals while it's all tenanted. So that's why this project had to be also design assist, because means and methods become really critical, moving the contractor forward. So we had Permis de Lisa brought in at the end of design development to work through a 10-month construction document phase. Adamson was the exec. And so again, the hypothesis here was that we would attach a conventional but folded unitized curtain wall system, like with this kind of geometry, where one of these would be a single panel, and it would be steel mullion reinforced to an aluminum section in order to span from here to here. Now, the floor to floor, the column spans about 30 feet, and you would think this building is strong enough to handle a curtain wall, right? Well, it's not. What we discovered was those precast panels on the wall were basically diaphragms that were spanning from column to column. They only had 4 points of connection, and all the loads went axially straight down the column lines. And the actual slab edge was only just like 15 inches of concrete spanning 30 feet. Like it couldn't actually take the weight of a new curtain wall because it was never designed to take anything at all whatsoever. And so we were like, okay, well, all that precast got to come off. So how are we going to hang this curtain wall? Well, we basically trimmed every single floor plate with a new piece of steel that replicated the load transfer of the original precast, which means we collared the columns, we x-rayed the rebar, we drilled in around where the rebar wasn't, and then we spanned that new steel. But the genius of that, as everyone kind of discovered after the fact, was we could pre-engineer every curtain wall bracket onto that prefabricated steel, all verified based on site survey, and the installation went so much faster than anyone thought. And the disruption to tenants was absolutely minimal because you've got 8 times less field drilling of coring through the slab to make all these reinforced anchors, which is often what you do. Anyway, the moral of the story is the whole thing was done for about $60 million. I am privy to the numbers, but I can't share them with you. But suffice it to say, Brookfield made a ton, an absolute ton. And surprisingly, 100,000 square foot floor plates are in demand. You wouldn't necessarily think it, but Amazon came in and took out, they say New York, they're not going into Long Island City, but they took 3 floors in this building, 300,000 square feet. And so the whole building re-rented out way above, again, their pro forma targets. And now Brookfield, I don't know if you know the building, but 666 Fifth Avenue, it's this beautiful 500-foot tower on Fifth Avenue that the Kushners were going to tear down and have Zaha do a 1,400-foot tower. So they had some financing issues, and that went away. They sold the building to Brookfield Properties, and Brookfield said, we're going to reposition it. They hired KPF, and we got that job. And now we're looking at doing an 800 feet, full reclad in Lower Manhattan. And it's a really interesting thing. Of course, you guys are all aware of the upgraded energy codes in New York City, which are really hardcore. And it's mandated, basically, now you have to start recladding your buildings with much higher performance envelopes, with all the bells and whistles, with better window-to-wall ratios, with kinetic systems, and so forth, in order to avoid paying, eventually, kind of a carbon tax moving forward, which is going to ramp up from 2025, 2035, 2050. Anyway, so it's a really nice building. This is crazy. It so happens in New York City that you have to do an integrated building maintenance unit track if your building is not orthogonal. So because this building folds, we did the first integrated curved concealed track in a folded curtain wall ever. And that's what this mock-up is. It's basically here, this is the integrated track that gets swallowed into the curtain wall mullion. And for anyone who's a geek out there, we basically push the air seal line back in order, like a race car, like the track could go to the outside and then corner around the air seal line, all in the drain joint cavity to the exterior, so the track could go through it. Anyway, this is being done in Spain. It got approved. This is our visual mock-up. up in Permis de Lisa's factory, which is on a rotating turntable, which is quite nice. So you can see your mock-up from any given angle of the sun, snow retention tracks, and their airplane engine test. This was done up in Montreal, and then the curtain wall fabrication up in Hartford, Connecticut. And then the installation. So here you can actually see the additional steel beams with the pre-engineered bracket locations. And then the whole thing is all done, all opened up. I mean, no one would ever design a building from scratch like this. So it had to be a reclad. So I'm just going to show you two more things. This one's a brief one. This is a commercial office building in Calgary. It's the tallest building in Western Canada now at 250 meters, 257. Also by Brookfield, but this was done design, bid, build, hard bid. And it's a very similar story to the Tishman Spire one. And believe it or not, Fumihiko Maki and Foster were in this competition, but they got beaten by Earl Arney of Arney Fender Castellitis out of London, teamed up with Dialogue. And he proposed a really friendly developer building. And you know, most kind of like all the World Trade Center towers today go floor-to-floor glass with a kissed transom that's concealed behind the glass, still with an insulated transom, but the glass is always going floor-to-floor, you know, into the 13, 14, 16-foot ranges. So this building does that, and then in that concealed zone above the kissed transom, it has an integrated shadow box. So it's very elegant, but the key point is 92% of all the panels are completely rectangular, vertical, and standard. And so even in the Canadian market, with the 25% discount for the Canadian dollar, Oldcastle won this bid, and the basic curtain wall came in at like $76 a square foot. But the corners are all conic. So we go from a super tight radius, widening up to a 5-meter radius at the top of the tower, and then we resolve into a radius crown that comes back down. And so that one part there is more like $300 to $400 a square foot. And so again, Brookfield, riffing off of the Tishman Speyer experience, said, well, that's our risk. So again, the tail wagging the dog, you have to be able to do conical curved glass in a bending tempering furnace of this scale with floor-to-floor height glass, with an aesthetic that they accept, a color rendering index they accept, and a solar heat gain coefficient that they accept with a VLT that they accept. It turns out there are 3 coatings in the world that met that criteria. It took a lot of research to get to that point and dial it in. And then, of course, they did commission the same glass companies around the world to build mock-ups. And what they wanted to see, and maybe just to make the point, is Brookfield would never accept the flat and the curved being even a slightly different coating. The idea that you would actually read the legibility of the corners being somehow even slightly different, no chance. And that's a pretty enlightened point of view. And so you had to nail the corner curved glass, and then it had to become the flat glass. And so all the glass was supplied, I think in this case, by AG Sear Europe, and then Cricursa did all of the curved glass. I believe Interpain did the flat fabrication, and then it all came together basically from the same batching. So here's the mock-ups we did here. We did the 3 different coatings from 3 different manufacturers. We did 1 curved conical panel and 1 flat panel, also to see whether those coatings would experience any optical differences from flat to curvature. And that was actually quite interesting too. And in this particular project, European fabrication proved to be neutral with Chinese fabrication. There wasn't actually a difference, which was interesting when you drill down on the numbers. There is a kind of global convergence in terms of the price of glass production and automation, even though there can be huge variation in the way people quote things. So these are the curved panel fabrications being done. Actually, this is done in Florida. So most of the rest of it was done in Canada. And then we had our performance mock-up. And then the actual tower installation. So it's kind of been recognized as a kind of shockingly disciplined tower with kind of World Trade Center 7-like transparency. It kind of oscillates between that being transparent versus being reflective, because the reflectivity on the glass is only about 22-23%. Whereas, for example, Maki's World Trade Center 4 is 45% reflectivity. It's basically the building is like a stealth building because it literally reflects everything around it. You can't see the building itself, which is kind of awesome. This atrium is pretty interesting as well. These panels are actually 10 by 20 feet, 10 by 20 feet curved and 10 by 20 foot flat with 10 by 20 foot skylights and with this custom steel frame all built by Sealy. We also have a large atrium roof, which is in here, which is all double curvature, which has cold form triple glazed skylight panels. Now, one of the bizarre things about this, I'll just tell you, is that, check this out. So this is half of the atrium. Because this parking lot was not allowed to be demolished until this tower was finished and its 5 levels of subgrade parking were brought online to make sure that there was no net reduction in the amount of parking in downtown Calgary. And it so happens they nailed the leasing on this. I think it was 72% pre-leased even before they started construction. But then, of course, the oil sands market collapsed and Calgary went into a bit of a funk. And now no one's probably going to build phase 2 of this master plan for probably another decade, which means this atrium is going to be living as a kind of half atrium, which is quite sad. But anyway, that's the economics of it. And then here's our 3-story crown, which everyone evaluated as a kind of occupied observation space, but the core didn't allow dedicated vertical transport, and the economics of the project didn't justify it, so they just kept it as an illuminated crown as opposed to an occupied space. But check this out. We're pretty proud of this. It's pretty nice. And then we're, one last project, the indefensible Morpheus Hotel in Macau. And so we've done quite a bit of work with Teahouse over the year, and on this project we helped them on the design side, and then we were novated over to the contractor side. So we worked for Kiatech, which is a Belgian curtain wall contractor, under Dragage, who is the main contractor, to deliver this envelope. And our scope of work included the enclosure metal panels to the exoskeleton steel. So the exoskeleton steel, you'd think, well, why couldn't it just be exposed? Well, the thing is, to make this steel efficient, some of them are tubular sections, some of them are square sections, some of them are wide flange sections, some of them are straight, some of them are curved. They all need to be fire protected, and they're all bolted connections from one to the other. So they all need expansion flanges that come out so you can actually connect them. So it was not a pretty looking exoskeleton structure. It's not like the New York Times where they could just intumescent paint everything and keep it all smooth and beautiful. So it had to be clad, and really Zaha wanted it to be clad. But it is a true exoskeleton, which is kind of cool. So it has 2 cores going up the 2 towers, which are about 40 stories. And then the exoskeleton is literally on the outside of the envelope, and the structure goes right through back to the core. So it's actually column-free spaces on the interior of the building. And then the exoskeleton gets this kind of like hyper-fidelity cut. These are all renderings, of course, of what it is now. So here's some of our kind of drawings. So we are taking a design surface from Zaha's, and we're taking Bureau-Happold's steel model. But now we are on the contractor side of the table. So we are now owning that. And we're now doing a complete engineering of the painted aluminum cladding, all of the rationalization to flat, single curvature, double curvature. We're working within the constraints of panel fabrication sizes, how to actually stud weld all that stuff, and how to subframe it all, and how to fabricate all that curvature, and lock it down onto the steel, onto like a constellation of literally thousands and thousands of custom welded cleats that have to go back on that steel. So we're in a place of basically owning the primary steel fabrication drawings, not the steel connection detailing. That's actually being done by the steel fabricator, but they are then sending us their data, and we are adding all of the welded cleats to it, which then go back to the steel fabricator, for them to weld it on faith that they're going to do it all correctly. And then when we come to site, all of our prefabricated panels lock and hook on correctly. And that actually was done beautifully. Now this process, I mentioned Elefront a couple of times. That's just our own in-house Rhino plugin that we've developed over 10 years because we used to do a lot of design build, that we self-perform a lot of work, and we sort of funded the evolution of tools for automation. And essentially, it's available for free on Food for Rhino, so all of you can play with it if you want. And there's some other tools that do some similar things. It's not exclusive. But we just put it out there because we figured, we're not a BIM software company. We don't really want to be in that kind of business. As you can say, Case, guys know the Case guys, David Fano and all them? Well, they thought it was better just to join WeWork. So we'll see how that works out. We're not doing that, by the way. So the point about Elefront is what it is basically a tool to attribute properties to Rhino objects, to create databases, to enable the interrogative overlay onto databases to extract subsets of data, which then we can hand out to other people to do different things. Also working with document templates, we can automate the creation of drawings. So we can make 10,000, 100,000, 1 million drawings. For this project, we have 1.6 million parts, including the G code. And all of that, we only had a team of 5 people, and if you didn't have automated tools, and if you didn't understand the associative rule-based knowledge of the system that you have designed, because it is that kind of industrial design domain that you need to own for any of those tools to actually really have any utility. I mean, most architects, they're limited to essentially geometric rationalization and space reservation as an offset for clash detection. But most architects are not detailing the actual sub-assemblies, the engineering of panel thicknesses and welds and so forth. So, that's why it's not appropriate to do that on the owner side. It's appropriate to do that for the contractor, where it has the need. But without those kind of tools, I don't think this really could have come into fruition. So a drawing like this is automated. We're not drawing this drawing. We're programming this drawing, and this drawing is being created out of data sets. And then, of course, again, my favorite expression of BIM pornography, all of these images are completely rhetorical because they themselves, as representations, have no utility except to communicate to you rhetorically how complicated it is. And so here's some basic data, 193,000 square feet, 23,000 fastener count, 4 million total parts, 1.38 million. Anyway, you get the picture. But that is the future. But the point that I did make, and I'm going to reinforce, is that the tools are only really powerful when combined with, I'm just going to say generically, domain knowledge. And I don't care whether you're dealing with space syntax or you're mapping the kind of like psychological properties of spaces on children or whatever it is that you're doing, you must have real domain knowledge and expertise and an understanding of all of that criteria in order to start utilizing these tools to actually kind of automate it. And this is where the Kateras of the world, the WeWorks of the world actually will put these tools to good use because they are vertically integrated. They understand that the future workflow comes from owning the design of something, right? It's a very interesting space to be in. Anyway, so a few more images here. Looks like a Geiger drawing. And all of this complexity just to generate a surface. So these are the double curve kind of panel templates. This is our mock-up, which is quite a nice mock-up. And this validated the tolerances that everyone was looking for. These are all the cleats that I was talking about that we're attaching to. And for whatever it's worth, it can be done economically. I wouldn't say it's cheaper than doing it flat, but it's possible. And I would say anyone who's ever seen this building is kind of shocked at the level of absolute precision of every one of these reveals and joinery and double curvature around the whole project. And with that, I'm going to stop and say thank you.